I'd like to graph some plane curves using parametric equations. Before we jump in with that, let me remind you about our definitions here. It says if f and g are continuous functions of t on an interval, then the set of ordered pairs f of t and g of t is a plane curve. The equations x equals f of t and y equals g of t are parametric equations for the curve, and t is the parameter. So we think of the curve as the path of a point moving along a plane, and the x and y coordinates of the point are a function of time. So let's graph some, and here will be our directions. For all of the parametric equations, I'm not going to have space for the directions, so I'm just going to show them this once. The directions will be sketch the curve represented by the parametric equations and eliminate the parameter and write the resulting rectangular equation whose graph represents the curve. So we're going to do two things: sketch the curve and rewrite the parametric equations as a rectangular equation. So let's start with this one. We'll have x equals 3t plus 2 and y equals 1 minus t. So let's start by finding some ordered pairs of points that would be on the curve. So to find those values of x and y, I'm going to put in different values for our parameter t. So I'm going to put some negative values and positive values, and as you do this, you can adjust the values of t that you put in. If you don't like the ones that you put in, or it's not illuminating enough, put in different values. But I'm going to start with -2 and -1, 0, 1, and 2. And again, if it's not enough, or if I feel like I need to put in t equals 5, then I would go ahead and do that. And I want the x value and y value that goes with each of these values of t. So I'm just going to substitute -2 in for t in this x value. So I'd have 3 times -2 plus 2, and that would give me -4. Let me just continue working with this x value. So 3 times -1 plus 2 would be -1. Put in 0. 3 times 0 plus 2 would be 2. Similarly, I put in 1 and I get 5. And I put in 2 and I get 8. Now let's move to our other equation. We're substituting in these values of t for y. So 1 minus -2 is 3. 1 minus -1 is 2. 1 minus 0 is 1. 1 minus 1 is 0. And 1 minus 2 is -1. So now I have some points that I can graph. So let's come over here. I'm going to just have the increments be by 1 here and by 1 here. So I'm starting with -4, 3. So -1, 2, 3, 4, 3. So 1, 2, 3. Do it relatively neatly, although you can see I did the grid by hand. So then we have -1, 2 right here. And I have 2, 1 right here. And I have 5, 0 right here. And I have 8, 5, 6, 7, 8, -1 right here. And you can see that it seems to be that these points are collinear, and I have something that looks like this. And we can tell the direction of the point. If we think about this representing a point traveling along this curve, at time -2 it's here, at time -1 it's here. Let's put in time 0, it's here, and then it moves on to time 1 and time 2, and on it would go. So to show the orientation, to show that the point would be going in this direction, we often put some arrows on so somebody could tell the orientation, and you would expect that to be part of the graph. When you're showing a plane curve, you want to show the orientation. Now it looked like it was collinear. Let's confirm that we have a line. In fact, let's remove the parameter so that we can see for sure, based on what we know about equations in rectangular form, for sure that this is a linear equation. So, and by the way, you could probably tell just by looking and seeing that the slope is consistent, and this was a line, so I don't think it takes much convincing to see that it's linear, but let's figure out what the rectangular equation is that would match this line. So we're going to solve for t in this equation right here. So I have y equals 1 minus t, and if I solve for t, I'm just going to put t on the left-hand side and subtract the y, and I have t equals 1 minus y. And now we can substitute that into our other equation so that we'll see the relationship between x and y. So I have x equals 3 times, and instead of t, I'm right, so here's my equation. Instead of this t, I'm substituting in that 1 minus y, and I have plus 2. So my equation is x equals 3 minus 3y plus 2. And if I put the x's and y's on the same side, I would have x plus 3y equals 5. And you know we recognize that, I hope, as a linear equation in rectangular form. Or if you prefer, you could solve for y and have y equals negative 1/3 x plus 5/3. And you can see that our slope is negative 1/3. Our y-intercept looks about like it's at 5/3. But now we have the rectangular equation whose graph represents this curve. Let me show you another set of parametric equations that I've already done that were very similar. So this was x equals 3t plus 2 and y equals 1 minus t. All I did in writing the next pair of equations was I replaced t with 2t. So this became a 6t, and this became a 1 minus 2t. And I've already done the work, but let me show you what happens. Here it is. Here's our equation, our set of parametric equations. I've already substituted in these values, so we wouldn't need to right now. But I put in negative 2, negative 1, 0, 1, and 2, just as we did in the previous problem. And I plotted those points. And you'll notice it looks very similar to the one we just did. Look at those lines. Y-intercept is about the same. The slope looks about the same. So, in fact, look at some of the ordered pairs. You see 2, 1. Negative 4, 3, 8, negative 1, they have those points in common. But do they in fact represent the same equation? So I rewrote this one in rectangular form as well. I solved for y here, just like we did in the previous one. I used this equation and I solved for t, solved for t. Substituted it into our equation that represents x. And solve the equation, and notice the equation was identical. Right here it is in standard form, there it is in slope-intercept form. So in fact, they are equations that have the same plane curve. But look at what's different. This is what I want you to see about parametric equations. They give you more than just, here's the graph. They give you some more information about the path of this point. Notice for both equations, t equals 0 was right here. But on the one on the left, t equals 1 is here, and on the one on the right, t equals 1 is here. They're both going in this direction, but notice t equals 0, t equals 1, t equals 2. This one is moving faster than this one. And that's part of what the parametric equations give you. What time a point is, the point, so to speak, would be at a particular place in the plane. Let's look at another pair of parametric equations. Let's use this one. So we have x equals t squared minus 4t and y equals t plus 1. Let's see what this gives us. We're going to plot some points. And we're going to put in values of t. And then we'll find our values of x and find our values for y. So if I started the same place I did on the previous one and substitute -2, -1, 0, 1, and 2, and I can see what I find. If I need to do more, I can do more, or find -3, or find +3, or +10, whatever I need. So let's substitute in -2. And let's find our x values first. Substitute in -2, -2 squared would be 4, and then -4 times -2. This is good arithmetic for us. We have 4 plus 8, that would be 12. Substitute in -1. -1 squared is 1. 1 minus 4 times -1 would be 5. 0, that makes the arithmetic easy. 0 minus 0. 1 gives us 1 minus 4 times 1, that is -3. 2 gives us 4 minus 8, that is -4. And let's find the corresponding y values. Arithmetic is a little bit more straightforward. Pop in -2. -2 plus 1 is -1. -1 plus 1 is 0. 0 plus 1 is 1. 1 plus 1 is 2. And 2 plus 1 is 3. Now let's plot these. And if this isn't enough, we can plot some more points. So let's see. 12, -1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. -1 is about right here. 5, 0, right here. 0, 1 is here. -3, 2 is here. -4, 3 is here. Now I'm looking at that and it doesn't feel like enough. I can see it's coming this direction. Is it going to continue up this way? Is it going to curve? Let's put in a couple more points. Let's put in a t-value of 3 and a t-value of 4. And let's see if that helps us figure out what this thing looks like. So we pop 3 in. 3 squared is 9. 9 minus 4 times 3 is -3. And we're substituting in 4. 4 squared is 16. Minus 16 is 0. Let's pop in 3 for y, or for t in the equation for y. We have 3 plus 1, that's 4. And 4 plus 1, that's 5. So now we have 2 other points to put on our curve. -3, 4 is right here. These increments are all by 1. And 0, 5. This is 1. This is 2. This is 1. This is 2. Of course, I should label those. So I have 0, 5. And you could plot some more, but what you'll find is it looks sort of like this. And I'm going to turn my paper so that I can draw this a little bit better. It's a little bit easier for me to draw this curve. It's coming down this way. And similarly, it's coming over here. So it kind of looks like a parabola. We can confirm or find out that that's not correct in just a moment. But let's see, what's our orientation? We have 0, 1, and then it went to -3, 2, and then it went to -4, 3. As your t values get bigger, our graph is going this direction. right? We started here at -2, we were at 12, -1, then we're at 5, 0, 0, 1, and we're moving our path in this direction. So we would want to show someone reading our graph that that's the look of the plane curve. Let's confirm that we have a parabola. So we're going to convert the equation from this parametric form. We're going to find the equation in rectangular form that represents this curve. So let's solve for t in one of the equations, and we'll substitute it into the other equation. I think I'm going to need a little more space than I have right here, so let me grab another piece of paper. So let's ooh, you can't see that very well. Have had that chopped off the whole time. Maybe. Oh no, I just turned my paper back. Well, we'll see. Here we go. We're going to solve for t here. So we have y equals t plus 1. So we solve for t. So we have t equals y minus 1. Remember, the goal is now we're eliminating the parameter. So we know t equals y minus 1. We substitute it in here. So we have x equals y minus 1 squared minus 4 times y minus 1. Let's multiply that out. We have x equals y squared minus 2y plus 1. And we have negative 4y plus 4. So we have x equals, let's combine our like terms, y squared minus 6y plus 5. And I hope you can recognize now that we definitely have the equation of a parabola that opens to the right. So that confirms that this is probably the correct in the way the graph looks. Let's do a little bit more. This is good practice. Let's put this in standard form so we can see where the vertex is. I prefer to have the quadratic part on the left. If that seems like a waste of time to you, then don't do that. That's just silly maybe to you. Then don't do that. But I'm going to complete the square with respect to y, so I'm going to subtract 5. Good reminder on how to work with our conic sections. Take half of 6, that's 3. 3 squared is 9, so I need a 9 right here. And of course, that means I'll add a 9 over here too. So I have y minus 3 squared equals x plus 4. And now we can confirm that we have a parabola that has a vertex at negative 4, 3 that opens to the right. Let's look back here. Yep, there it was, right here. This is the point. This is negative 4. This is 3. So we have our equation in rectangular form. But notice from this equation, one thing that you lose is the orientation. You wouldn't know the path of the point was going in that direction. Let's look at the next one. I want to show you a way in which I changed the equation. I replaced t with negative t. So I'm changing the equation. So this became that, well, the t squared doesn't change when you put in a negative t. So this became a plus 4t, and this became a minus t. And let me show you how it looks. I already did the work. So because the work is so similar, you can pause this video and look at it a little bit longer if you'd like. Make sure I don't chop off the top of the equation this time. And notice I put in these t values, and here are the corresponding x and y coordinates. And here's what I want you to notice. This time, the orientation is in this direction, right? As t gets larger, the points on the curve are going in this direction. But you can also confirm that you have the exact same curve by rewriting the parametric equation, by eliminating the parameter in the parametric equation. And so I did this. So again, a duplicate of the work that we just did on the previous problem. Notice I solved for t. Substitute it into the other equation, and we ended up with x equals y squared minus 6y plus 5, which is the same thing that we had right here on our previous equation. So in fact, they are the same curve, but the orientation is different. We know the path of the curve is, path of the point is in this direction on this problem, but it was in the other direction in the previous problem. Let's do another problem. Let's let our next set of parametric equations be this. It's x equals 2 sine t and y equals 6 cosine t. Make sure you can see the equations. And notice there's a restriction on our parameter. We're only going to let t go from 0 to pi, so what would this look like? Well, let's find some values. We're going to put in values for t, and we're going to find the corresponding x and y values. So I'm going to put in some values that we can calculate easily. So let's put in 0. Let's see, we're going from 0 to pi. So I'm going to put in 0 and pi over 2 and pi. Those for sure. Let's use a value between these. I'm going to use pi over 6 just because I like the value when I substitute it into the sine function. So I'll put in pi over 6. And you could pick something different. And similarly, I'll put in 5 pi over 6 here. You could pick other values. Those are just the ones that I chose. So substituting 0 in to this equation, we know the sine of 0 is 0, so 2 times 0 is 0. We know the sine of pi over 6 is a half times 2 is 1. We know the sine of pi over 2 is 1, 1 times 2 is 2. Sine of 5 pi over 6 is 1/2 times 2 is 1. And the sine of pi is 0, and 0 times 2 is 0. So those are our values for x. Let's find our corresponding values for y. Substitute in 0. The cosine of 0 we know is 1. 6 times 1 is 6. Cosine of pi over 3 is square root of 3 over 2. Square root of 3 over 2 times 6 is 3 square root of 3. Cosine of pi over 2 is 0, and 0 times 6 would be 0. Cosine of 5 pi over 6 is negative square root of 3 over 2. Multiply that by 6, and we have negative 3 square root of 3. And we'll substitute in pi. Cosine of pi is negative 1, and negative 1 times 6 is negative 6. So we have some ordered pairs to look at. And again, as with the previous example, as I mentioned, you can refine this. We could put in other values between 0 and pi if we needed to. But let's see if we need to. Let's see what this looks like. I'm going to start. Now, I don't even need these t values as I'm plotting the points at 0, 6. So 1, 2, 3, 4, 5, 6. So I know the point is starting here as t values get larger and larger. Let's see. I know. Let me go to 2, 0 next. 2, 0. And then I'm going to go down to 0, negative 6. So here's 2, and here's 6, and here's negative 6. So somehow the curve, or the point, would start here and travel in this direction. What happens in between here? Does it come way out here? What does it do? Let's see. If you calculate 3 times the square root of 3, let's see. Let's punch that in. 3 times the square root of 3 is about 5.2. So this would be about negative 5.2. So at 1, we're at about 5.2. So here, similarly here. So it seems to look something like this. And you could confirm by plotting other points, with our orientation being this direction. And this is 2 right there. You can't really tell that. Let's eliminate the parameter and see what shape this looks like. Can you tell what it looks like? Let's see. In the previous problems to eliminate the parameter, we solved for t and then substituted in. I'd prefer not to do that on this problem. But what we do have is our trig identities. We know that for every value of t, the sine squared of t plus the cosine squared of t equals 1. That is always true. Well, what is the sine of t? Look back here. If we were to solve for the sine of t, I didn't leave very much space for it, but you can see, I hope, that the sine of t equals x over 2. And similarly, the cosine of t equals y over 6. I can substitute those values in for sine and cosine. So sine is x over 2, so let's write that as x over 2 squared, plus cosine of t is y over 6, and that's squared. Now if we do the squaring, we have x squared over 4 plus y squared over 36 equals 1, and I hope you recognize that this is the equation of an ellipse. Oh, and you see that we have a portion of an ellipse. The right-hand side, the side where x is between 0 and 2. And our y value is between -6 and 6. So this is the equation, of course, if we restrict those x values. Don't let them become negative. And we have an equation in rectangular form that represents this part of our ellipse. Let's do one more problem. Here are the parametric equations. You know, maybe let's not plot points first. There's nothing that says that you have to do that. Sometimes it's handy if you know what the graph looks like, and then we can figure out the orientation, see what the path is. And let's use the same idea that we did with the previous problem. I see sines and cosines, and by the way, notice that I have the parameter as theta instead of t. That doesn't change what we do at all. It's just that we're using theta instead of t. So we know with respect to this problem that x plus 4 is equal to the cosine of theta. And this is y minus 2 equals the sine of theta. We know that sine squared theta plus cosine squared theta is always equal to 1. And I just realized I didn't copy down the problem quite the way that I wanted it. So I'm going to make a change. There's nothing wrong with this problem, by the way, but it isn't quite as entertaining as the one that I wanted to do. So I'm going to change it right now. This is not quite what I wanted. I'm going to squeeze in a 3. X equals -4 plus 3 cosine theta. So I'm going to pop a 3 in here. We'll leave that a 1. But I'm going to pop in a 3. So that means we have 3 cosine theta right here. I wanted it just to be a little more complex for you. So we're going to divide by 3. So we have x plus 4 over 3 equals cosine theta. So a little more complex. Not too bad though. So when we substitute in our values, we have y minus 2 fourth sine. So I have y minus 2 squared plus cosine squared. We have x plus 4 over 3 squared equals 1. Now let's rewrite it. I'm going to square the 3 in the denominator. I just prefer it. And I'm going to switch these around, again, because I prefer it. So I'm going to have my x plus 4 squared in the numerator over 9 plus y minus 2 squared, you know that's over 1, equals 1. So I hope you recognize this as another ellipse. This time there is no restriction on the theta, so theta could be any real number. So let's draw this ellipse, and we'll make sure that we put the center at -4, 2. So -1, 2, 3, 4, 1, 2. Here's center. In the x direction, we'll go 3 units to find the endpoints of the major axis. So 1, 2, 3. 1, 2, 3. Right? So here's -4. This is -1. This is -7. In the y direction, we'll just move 1 unit to find the endpoints of the minor axis. So we're going to go up 1 and down 1. And then I draw as smooth an ellipse as I can through these points. Whoop. And it looks something like that. But now let's make sure we have the orientation for this particular problem. Let's put in some values for theta and find our values for x and y. Let's just use 0 and pi over 2, pi, 3 pi over 2, and 2 pi. Some of those that we're very comfortable with, I hope. So if we put in 0, we're right here. We know the cosine of 0 is 1. 1 times 3 is 3. 3 plus -4 is -1. So I'm substituting it into this equation right here. Don't forget there's a 3 squeezed in there. Let's put in pi over 2. We know the cosine of pi over 2 is 0. So it makes it -4 plus 0. Pop in pi. We know cosine of pi is -1. So we have a -4 minus 3. That's -7. 3 pi over 2. Cosine of 3 pi over 2 is 0. -4 plus 0 is -4. And then we're at 2 pi. Again, cosine is equal to 1 at 2 pi. So we have -4 plus 3, which is -1. Now let's play the same game over here, finding y values. The sine of 0 is 0. 0 plus 2 is 2. Sine of pi over 2 is 1 plus 2. Sine of pi is 0 again. Sine of 3 pi over 2 is -1, so we have 2 plus -1. And last we have 2 pi again. Sine of 2 pi is 0, so we have 2. So let's look at how this is taking shape. At theta equals 0, we're here at -1, 2. As theta gets larger, we move to -4, 3. Oh, so we're moving this direction. In the previous ellipse, we went clockwise, and it seems now -7, 2. We're going counterclockwise. And now we're from -7, 2, we move to -4, -1, and back this direction. And if you continued putting in values, it would just keep following the ellipse around on that curve. The plane curve would just, the point on this would keep going around and around, following the path of the ellipse. I hope you have the opportunity to practice graphing some parametric equations. Make sure you include the orientation and practice eliminating the parameters so that you can find a comparable rectangular equation that represents the curve.